Good morning, friends. Today I like to discuss about the charge neutrality in PN junction diode. Basically, in the thermal equilibrium, the semiconductor crystals is electrically neutral. The electrons are distributed among various energy states, creating the negative and positive charges in equal amount. And so therefore, the overall crystal is neutral. For this, there is the level of donor and acceptor atoms and its ion concentration. So if N of D and N of A are concentration of donor and acceptor atoms, and ND plus and Na minus are concentration of ionized donors and acceptors. Then the charge neutrality condition is expressed by equating the density of negative charges to the density of positive charges. Suppose N0 Na is equal to P0 and Nd plus. This N0 plus Na minus Pa. Pa is equal to P0 plus this Nd minus small nd. Nd minus small ne, where N0 and P0 are thermal equilibrium concentrations of electrons and holes in the conduction and valence band. Conduction and valence band. The parameters Nd is the concentration of electrons in the concentration of electrons in the donor energy state. So ND plus is equal to capital small d, n small d is the concentration of positively charged donor states. Similarly, P and P and other whole concentration of acceptor is expressed as Na minus is equal to Na minus Pa. For accepted atom, so it is N0 plus Na is equal to P0 plus N of D. We have the law of mass action, as Ni square is equal to N0 into P0. That is N0 plus Na is equal to Ni square upon N0 plus Nd. That is P0 is equal to Ni square upon N0. So putting the value of P0 as Ni square upon N0 and solving this equation are N0 square plus N of A, this N0 square, this is N0 is equal to Ni square plus Nd into N0. So N0 square plus Na minus Nd, N0 minus Ni square is equal to 0. So this is a quadratic equation. This is a quadratic equation in N0 square. So there are two roots, and the roots are N0 is equal to this is Na minus Nd of this by 2 minus plus under root Nd minus Na whole square divided by 4 minus 4ac, that is plus 4Ni square. 4Ni square. So this is x is equal to minus b plus minus under root b square minus 4ac divided by 2. So the roots from this part. For n type, Na acceptor is equal to 0. That is, the root equation can be written as N0 is equal to Nd donor by 2 plus under root Nd square by 4 plus 4 Ni square by 4. So this is Nd by 2 plus under root nd square by 4 plus ni square. So this is majority charge carrier, that is N0 is majority charge carrier. Now the minority is P0, that is Ni square by N0. So this can be expressed with the help of the equation, and if we put N0, N0 is equal to Ni square upon P0, then this is N0 plus this N0. In place of N0, we can write this is Ni square upon P0 plus Nd is equal to P0 plus Na. So this Ni square is equal to P0 square plus Na minus Nd into P0, or P0 square plus Na minus Nd P0 minus Ni square is equal to 0. So again, this is the quadratic equation. This is the quadratic equation in P0. And the roots are minus b plus minus under root 4b square minus 4ac divided by 2. So this kind of the equation is there, and its root P0 is equal to minus Na minus Nd by 4 plus under root Na minus Nd whole square by 4 plus Ni square. So in this case, P type, for P type, we have N donor is 0. So P0 is minus N0 by 4 plus under root N0 square by 4 plus Ni square. So these are the charge neutrality condition, and having the concentration of majority charge carriers as well as minority charge carriers. Now the graph of this case, is suppose this is the carrier concentration and here it is the temperature. This is temperature and here it is carrier concentration. This is N0. So if we take this gap for the scale, so this is 100, here it is 200, 300, 400, 500, 600, 700 Kelvin, and these are the concentration per meter cube. So the graph is something this way. then there is a flat over this point, and then this is the case. Here it is this extrinsic semiconductor, and at high temperature this is intrinsic semiconductor. We can have explore as Ni, intrinsic, and in this case it is partial ionization. So this part is A, B, C, and D. So AB segment at low temperature, AB segment of low temperature is partial ionization. Partial ionization. BC segment is extrinsic semiconductor, and CD is intrinsic semiconductor. Extrinsic semiconductor at high temperature. At high temperature. Now, when the bands are formed, then during that part, band structure of an open circuit PN junction. So if you take this consideration, that is P type, then it is here N type, P type, and here it is N type. This is the valence band. This is the valence band. And this one is Fermi level. This is the Fermi level. So what we feel, the initial Fermi level, this one is the initial Fermi level for EI. Here it is EI. And then this is, if you see, this is F, Fermi level in P side. This is Fermi level in N side. This is the Fermi level of N side. So this side Fermi level is going down. Here the Fermi level is going up. This is rise. This is rise, and here it is fall. Rise and fall of the Fermi level. So if we name it, that is E of valence in P type, E of conduction in P type, so E of conduction in N type, E of valence in N type, So this energy level difference, is E0. Energy level difference is E0. So this energy is E1 Here it is E2. Again, the same difference of energy level. Here it is E0. This is E0. So the Fermi energy level EF is closure in conduction band in N-type ECN and closer to the valence band, in P-type material. P-type material. So we can have the shifting, the shift in energy level, E0 is indicated as E0 is equal to E1 plus E2. E1 plus E2. That is E0 is equal to ECP, conduction band, minus ECN, the difference. And also this is equal to E0 is equal to EVP minus EVN. So this is in reference to conduction band and here in reference to valence band. So this E0 represents potential energy of electron. So the potential developed across the junction due to the energy expression, as EF minus EVP is equal to 1/2 EG minus E1, half of this. And this ECN minus EF, that is in case of the N-type. This is 1/2 EG minus E2. This is equation 1 and this is equation 2. So adding both the equation, we have this EF cancel. So we have ECN minus EVP is equal to this one we added EG minus E1 plus E2. This is equation number 3. So E1 plus E2, E0 is equal to E1 plus E2 is equal to EG minus ECN minus EVP. This is equation 4. So E0 is equal to how much? This E0 is equal to EG minus ECN minus EVPN. So this is, we also have the expression as EG is equal to KT ln NC NV upon NI square, equation 6, EC N minus EF is equal to KT ln NC by ND, and this is EF minus EVP is equal to KT ln NV minus upon NA. This is equation 7, and here is equation 8. Substituting these values, in equation 3 or equation 5, we have this E0 is equal to KT ln NC NV upon NI square minus KT ln NC upon ND minus KT ln NV upon NA. That is equation 9. So if we take KT common and then we operate, that is ln NC NV upon NI square minus ln NC upon ND minus ln NV upon NA. And this is KT, this is KT ln NV NC ND NA upon NI square NC NV. So this is KT ln ND into NA divided by NI square. So this is E0, and V0, the potential is E0 by E, that is KT by E ln ND NA upon NI square. So this value is 26 millivolt ln ND NA upon NI square. So this is the contact potential. This V0 is contact potential. That potential will be developed across the junction. This potential is developed across the junction, and if ND donor is equal to N0, this is equilibrium electron carrier concentration, and Na is equal to PP0 equilibrium whole carrier concentration, and Ni square is equal to N0 P N0 is equal to PP0 NP0. This is. So we can have E0 is equal to KT ln. This is ND NA, that is NDNA upon Ni square is equal to KT ln NP0 N this is NN0 and this is PP0 divided by NN0 into PN0. So this is cancelled and here it is KT ln PP0 KT ln PP0 upon PN0 and also E0 is equal to KT ln NN0 upon NP0. So one is majority upon minority. The subscript O is added to the concentration to indicate that these are obtained under the condition of thermal equilibrium. Thermal equilibrium. Now one can have the diagram. Suppose this is P type and here it is N type. So this P type is something this is PP0. That is the majority charge carrier of hole. Or here it is PN0. This is the minority charge carrier. Minority charge carrier, here it is majority charge carrier. Similarly, in case of electron, if this one is the NN0, majority of electron will this is the electrons and this electron is NPO. It is minority. And this particular is CDR. So what we take, this is NN0, equilibrium concentration. equilibrium electron concentration, that is ND here. This is Ne, that is whole carrier concentration, that is Na. This is the whole carrier concentration. So electrons and holes, as it case may be from one side to another side. So these are the variation of charges from one side to another side in the carrier concentration and its charge neutrality. So thank you for this lecture. Thank you.